In the last segment, we introduced the concept of conformations of cyclohexane, and we learned that the so-called chair conformation is the most stable, lowest energy conformer that cyclohexane can adopt, because that allows the bonds to be staggered in order to minimize the torsional strain within the molecule. And in this segment, what we're going to do to follow up on that is, rather than looking at a molecular model as our sole tool for evaluating and understanding chair conformations, we're going to learn how to draw chair conformations on paper, because of course many times it's not going to be convenient to carry around a backpack full of molecular models in order to explain concepts related to cyclohexane and the shape that it adopts preferentially. Instead, it's going to be useful to be able to draw out these concepts on paper. So we're going to learn today how to go about drawing chair conformations of cyclohexane. By the end of this discussion, you should be comfortable with drawing chair conformations of cyclohexane, as well as the ring-flipped versions of the chair conformations that you draw. So to get started on this, what we're going to do is look at how to go about converting something like what we see up top here, our chair conformation, which is pretty reminiscent of what we built a molecular model of. And reminder, the reason that we call it the chair conformation is because hopefully it looks to you somewhat like someone sitting in a Chase lounge chair. I know that requires some imagination, but we can kind of map out the parts of this Chase lounge chair. And we would see that there are 6 bends and ends of the line representing the 6 carbon atoms of the ring. And you can see that the Chase lounge chair is kind of bent up, sort of like the chair conformation atoms that you see in cyclohexane, which we're outlining here in blue up top. So what we're going to try to do today is we're going to establish how we can make this chair conformation, rather than using a ball or stick model like we see here, or the balls and sticks from the actual physical molecular models we looked at in the last segment, to drawing these out on paper. You'll notice that both in the bottom image of the guy in the chair and the top image of our chair conformation ball and stick model, we have the same sort of structure showing up in each of those. And that is, we have this 6-membered group that looks something like this, or alternatively, if we're rotated around the other way, something like this. So we're going to learn how to use those sorts of templates today to represent the fact that the bonds relative to each carbon atom are staggered, and we're going to allow us to show which groups are axial and which groups are equatorial. Remember that the axial groups are the ones that point straight up or straight down. We can recognize those by going to, say, the carbon in the upper left-hand corner here and seeing this group is pointed straight up, so we describe that as axial. On the next carbon atom, there will be a group always that's pointed straight down in the chair conformation that is also axial, so axial down. We come to the next carbon, and there's a group pointed axial up. Next carbon, there's a group pointed axial down. Next carbon, axial group pointed up. And finally, on to the very last carbon, so we follow over to the left to the next carbon atom here in black, and we go down, and that's going to be our last group that's axial down. So you'll notice that going around the ring, the pattern is at each individual carbon atom, there's a group that's axial up, axial down, axial up, axial down, all the way around the ring. And that's one thing that we will need to represent in the chair conformation diagram that we are able to make on paper. Additionally, we will need to be able to show the equatorial groups. Those are the groups that are angled slightly up or slightly down. And what you'll notice in the molecular model here of the chair conformations, if we start in the upper left corner, we describe this group in green as being equatorial, oriented slightly down. At the next carbon, to make sure that bond is staggered relative to the one prior to it, the group we would describe as equatorial, but it's angled slightly up. We come over to the next carbon in the ring. Our equatorial group is angled slightly down. Over to the next carbon, equatorial is slightly up. Next carbon, equatorial is slightly down. You're probably seeing a pattern here. Next carbon atom and the very last carbon of the ring, equatorial is oriented slightly down. So you'll notice that in order to stagger the bonds, the pattern as we go around the ring from one carbon to the next is that the equatorial group is oriented slightly down, slightly up, slightly down, slightly up, just like the axial groups are oriented straight up, straight down, straight up, straight down as we go from one carbon atom to another. So we'll definitely want to reflect this in the chair conformation diagram that we show, because we need to be able to illustrate on paper which groups are axial, which groups are equatorial, and what the relevance of that is. So that's going to be our objective here as we go through. The type of structure and diagram that we're going to draw is going to be very reminiscent of what you see on the left-hand side of your page right here, where on the left-hand side of the page, each of those hydrogen atoms that are shown straight up or straight down are described as axial, And you'll notice that pattern of starting at carbon number 1 in the upper right corner there, axial is up. At the next carbon, carbon number 2, axial is down. At the next carbon, carbon number 3, axial is up. And you can recognize which groups are in front and which groups are behind so you don't get confused about that by keeping in mind that if you see a broken line, such as right here, see how the pink line or red line is broken, that indicates that that group goes behind the black line that's shown in front. Similarly, if we take a look at carbon number 3, the pink group here is in front of the black line that is in back, because we see that that pink line going straight up is in front of where there's a dashed or broken line in black behind it. So we're going to learn to draw these groups out on paper and create diagrams such as what we see on the left here, which is totally representative of the molecular model that's pointed out on the right, including how the atoms are color-coded, with the axial groups in this diagram being red and the equatorial groups being green. We're also going to learn how to go about ring flipping this molecule to take all those red axial groups and make them equatorial, and all the equatorial groups and make them axial. So let's get started on drawing the steps for drawing these chair conformations. We're going to walk through the steps required to draw a chair conformer. So what you see toward the top of the screen are the two different templates that we can use for drawing chair conformers. Those represent the two different ring flipped versions of a cyclohexane. Remember that we achieve the ring flip by rotating around the carbon-carbon single bonds to go from one chair conformer to the alternative chair conformer for that particular molecule. Each cyclohexane derivative will have two different possible chair conformations. So we're going to learn how to go about drawing these molecules. What we're going to start with in order to enable us to draw in structures like these up top here is we're going to highlight a few features of these and how we go about drawing those. So to begin drawing these structures, what we're going to start by doing is drawing the two lines, the two bonds here, here and here, or here and here. And I'm going to go through the procedure for drawing just the structure on the left, because the procedure for drawing the structure on the right is exactly the same, except you can see that the structure on the right is sort of, you could think of it as leaning the opposite direction of the one on the left. So we're going to go through the process for drawing the structure on the left, and the first thing we're going to do is we're going to start by drawing those two parallel lines that I've highlighted in gray up in the structure on the top. And as I mentioned, they absolutely need to be parallel to one another. So that's what we're going to do here, is just draw two lines that are angled slightly up and to the right, like so, that are parallel to one another. That's going to be the first step of drawing these, and those represent two bonds in the molecule that if you were to look at the chair conformation of cyclohexane, you would see that those would be parallel to one another in the molecular model. Then we're going to go in and draw two additional bonds in blue here and here that will also be parallel to one another. So we're going to draw two bonds. I want to try to make these as equal in length as possible that are parallel to one another. So the two blue lines should be parallel to one another, because those bonds are going to be parallel to one another in this staggered conformation, the chair conformation that we would achieve for this molecule. And finally, to fill in the last bit, we're going to draw two lines in green here to connect that would be parallel to each other. So those two green lines should be parallel to one another as well to give us the chair conformation of cyclohexane. So in order to plug on the substituents, the groups, onto this ring, whether they be hydrogens coming off or branches that are more complex, such as a tert-butyl group or an aldehyde branch coming off, or whatever you like, we need to go in and fill out those aspects of the molecule as well. So what we saw earlier was that the axial groups are going to point straight up or straight down on alternating carbon atoms. And so we're going to start in either the upper left or upper right corner of the molecule by drawing a group that will always be axial up. So we'll go ahead and anchor our molecule right here with a group that is axial, always, and pointed upwards. I'm just going to put axial in parentheses up. And then we're going to alternate going around the ring where each carbon atom has a group that is axial up, the next one has a group that is axial down, and so on and so forth, going all the way around the ring. So we went axial up to start with, so our next group is going to be axial down. And the main thing here is make sure those groups are pointed straight up or straight down. The next carbon atom here is going to have a group that's axial up, and that group is going to be in front of the carbon bond in blue that is at the back of the molecule, so I'm putting that black line in front of the blue line since it would be in front of it in the molecule. Then next up, axial down going around the ring, axial up, and then finally axial down. So you should see as we go around the ring that the pattern is up, down, up, down, up, down. So all of those groups that we see in black represent our axial bonds. And those axial bonds are alternating up and down. Now what I'm going to do is go ahead and draw in my equatorial bonds. And I'm going to show my equatorial bonds here as the last remaining color in my palette that I haven't used in yellow. And the equatorial groups are going to also alternate up, down as we go from carbon to carbon in the ring, but they're not going to be straight up or straight down. Instead, they're going to be angled slightly up or slightly down. So we'll start in the upper right corner again, and this particular bond is going to be angled slightly down, and it should end up being parallel to the bonds that we have in blue here. So we've previously made this bond in blue and this bond in blue, and that yellow bond that we've put to a hydrogen atom or whatever branches coming out the ring should be parallel to those. That's how we end up making this molecule staggered. Then when we come to the next carbon out of the ring, rather than the equatorial bond being angled downward, it's instead going to be angled upward, and it should match the bonds that are green within the ring. So here and here should be parallel to this bond that we're making out here. We go onward within our system here, continuing onward to the next carbon out of the ring. Since our equatorial group at the previous carbon was slightly up, this one's going to be slightly down. And if we draw this exactly correctly, it should end up being parallel to the two bonds that we see in red. So we always look pretty much 2 bonds away from the bond that we've just drawn here that's equatorial, and we should see that those bonds that are 2 bonds away, in this case the 2 bonds in red that I'm highlighting, should be parallel to that one that we've just drawn out equatorial. On to the next bond. The next equatorial bond should certainly be angled up, and I'm going to go ahead and draw that out in yellow just like I've drawn the other ones in yellow here. So angled up. And that should be parallel to the bonds within the ring that we've highlighted in blue. That's the bonds 2 bonds away. Next carbon atom, equatorial group, is going to be angled downward, so we go ahead and fill that in. And then finally, last but not least, this carbon atom's equatorial bond should be angled upward, which we're saying upward relative to the carbon atom that it's bonded to. So with that, we've gone ahead and we've drawn the entire template for making a chair conformation. If we were drawing the ring-flipped form of this molecule, we would instead have our bonds oriented opposite that, as I've circled there in the upper right corner, but we would still keep the orientation of the axial groups and the equatorial groups the same. Axial is always going to be straight up and straight down. Equatorial is angled slightly up and slightly down as we go around the ring, alternating between angled up and angled down to make sure that the bonds all the way around the ring are represented in a staggered fashion. Now that we've drawn a general staggered template or a chair conformation for cyclohexane, what we're going to do is show how we can go about flipping the ring. And remember that we do a ring flip by just rotating around carbon-carbon bonds to go from one staggered conformation to the alternative staggered chair conformation of cyclohexane or cyclohexane derivatives. So to illustrate this, what we're going to start with is 1-methyl cyclohexane, and then we're going to go about flipping the ring for this particular molecule. So we're going to go ahead and draw the first chair conformation, which we make the template just as we did using the guidelines just a moment ago, where I'm drawing in my required lines that are parallel to one another within the ring to make my 6-membered ring. Then I'm going to go in and draw in all my axial bonds, starting in the upper right corner, going axial up, and then going around the ring, alternating up, down, all the way around that system. And for emphasis here, that the hydrogen atom or the bond here is in front, I'm going to erase just a little bit to the left and right of that bond that's going vertical there so that we can see that that bond in black in the front middle is in front. Another way that this is commonly shown in these illustrations is to make the 2 bonds within the ring here at the front somewhat bold. So if you see that these are in bold or kind of shown as wedges is another way to think of it. That's to further emphasize that those bonds are in front. They're in the front of the molecule aimed at you. So now we have our 6 axial groups fused to our ring. And what I'm going to do next is fill in my 6 equatorial groups. And I'm going to show the equatorial groups in blue here just for emphasis. So we start with equatorial down, then we do equatorial up, equatorial down, equatorial up, equatorial down, equatorial up. And now we have our 6 equatorial groups on there. And we mentioned that we're going to use as our example here for doing a ring flip 1-methyl cyclohexane. So we should be able to fill in here our 1-methyl group. And it's very common, not always the case, but commonly the case that the methyl group or whatever you're putting there at carbon number 1 is located in the upper right corner of the molecule. So that's what I'm going to do here. And for the moment, we can put that methyl group either in the axial or the equatorial position. So I'm going to choose just arbitrarily here to put it in the axial position. We could have just as well put it in the equatorial position, be aware. It would have created the same molecule one way or the other. And to dot all my I's and cross all my T's, I'm just going to fill in my hydrogens here at the end of each line. There should be a hydrogen, filling those in yellow. So just plugging all those in, because technically if you're doing a line angle formula and you don't put anything at the end of the line, it would indicate that that's a CH3 group at the end of the line, because it implies there's a carbon there. So we plugged in hydrogens to emphasize that these are all bonds to hydrogen here. Now what we're going to do is the ring flip. And the ring flip I'm going to represent with an equilibrium arrow, because the ring flipping is a physical process, and at equilibrium what would happen is that some fraction of the molecules in a container would adopt the chair conformation on the right, some would adopt the chair conformation on the left, and some would adopt higher energy conformations altogether. These chair conformations are the lowest energy, the 2 lowest energy conformers, but certainly not the only number of ways that we can rotate around carbon-carbon bonds. So we take 1-methyl cyclohexane, we do that ring flip, which indicates we're rotating around carbon-carbon bonds to arrive at the second possible chair conformation, the second possible staggered conformation of this molecule. And in order to illustrate that we've done a ring flip, what I'm going to do is, rather than orienting the molecule like we've done on the left, instead we're going to show it oriented in the opposite direction. So I'm just drawing in my chair template here, and I'm still going to fill in my axial bonds just as I did before. I'm going to show my axial bonds in black, and my upper corner on the upper left and upper right, those axial bonds will always be pointed straight up, so that helps orient us. So I've pointed those straight up. Then I go around the ring, filling in that pattern of straight up, straight down, straight up, straight down. And again, for emphasis here, that the bond right there in the middle is in front. I'm going to erase just a little bit to each side of it to illustrate that that bond that's vertical there in the middle is in front of the atoms behind it. So I've put in our 6 axial groups. Now I'm going to go ahead and fill in my 6 equatorial groups in blue. And those 6 equatorial groups we're filling in using the same strategies that we used for the other chair conformation in terms of where to place those. So I'm filling in all of those like so. Trying to get all my bonds properly parallel to the bond within the ring that's 2 bonds away from it. So we've now drawn in our 6 equatorial bonds, and those should be set up so that they're angled down, angled up, angled down, angled up as we go around the ring. Now, in the ring flip, by convention, the way that we will show the ring flip is that when we go from the structure on the left to the one on the right, where we show carbon number 1 is going to change from that upper right corner to this lower right corner. So we'll show that as carbon number 1 and go around the ring from there. And additionally, when we do a ring flip, by definition, what the ring flip means is that we've rotated around so that all of the axial bonds become equatorial, all the equatorial bonds become axial. So we're going to, when we do the ring flip, switch all our axial groups to equatorial positions. All our equatorial groups are going to go to axial positions. And since we said that carbon number 1 right here, once we flip the ring, by convention we place it there in the lower right corner. we are going to take that methyl group, and it started off its life as axial in our initial structure, so now we better put it at an equatorial position. Our equatorial bonds here on the right are shown in blue. So we're going to go ahead and at that structure on the right where the equatorial bonds are shown in blue, we're going to put the methyl group right there at position number 1. The rest of those positions we can fill in as hydrogen, so I'm just going to quickly sketch in those, dot all our I's and cross all our T's here. So I'm just filling in all of those hydrogens at the ends of each of these lines, and voila, we are done with that. So you'll recognize that anytime we do a ring flip, the way to recognize that a ring flip has taken place is that definitely you should be able to describe that anything that was axial to start with, such as here, has become equatorial in the final structure. And that will be the only thing that changes about the molecule overall. You're not going to be adding any extra groups or anything like that. It's just axial becomes equatorial, equatorial becomes axial, and switching from one of these conformers to the other. So in the next unit, what we'll look at is how we can determine the relative energies of a ring-flipped version of the molecule. In other words, are these two structures that we've drawn equal in energy, or is one of the chair conformers even more favorable than the other?